So on an ideal day, I would have waited for the answer from the class, but let me tell you what people think might have happened is that the photosynthesis started happening. The plants started making oxygen, and that oxygen reacted violently with the metals. In the end, what we have is right now, most of the metals are in the form of MXO, right? Some metal oxide. So the point is, if you want to get the metals from the metal oxides, you need to do a redox process, because when the metals get oxidized, the oxygen is 2 minus or whatever it is, N minus charge, and the metal will be N plus charge. So what you need to do is you need to reduce these metals from the oxidation state, higher oxidation state, to zero oxidation state, which means you need to supply a lot of energy. So although the metals have been like this for billions of years, it's only maybe about 2,000 years ago or 3,000 years ago, what people have done accidentally is they were able to reduce this, the metal oxides, with the help of what we call the carbothermal reduction. So let me show you what people have done accidentally. When the when you take, for example, copper oxide, when you react with carbon, charcoal, what happens is you get copper metal and carbon monoxide gas. So just mixing copper with carbon with copper oxide is not going to cut it. What you need to do is you also need to supply a lot of heat. So this process is what we call in industry carbothermal reduction. In principle, you should be able to use this technique to extract all the metals, although the temperatures required for each metal is different. For example, copper, it takes about 900 degrees. Zinc might happen at about 600 degrees. But if you go to iron, you need to apply very high temperature. By the time you come to aluminum oxide, so if you want to do a carbothermal reduction of aluminum oxide to get aluminum metal, you need to apply temperatures in excess of about 2000 degrees Celsius. That's extremely high temperature. So copper, on the other hand, requires low temperature, while the aluminum oxide requires extremely high temperature. The big problem with such high temperatures is at this temperature, most of the aluminum oxide sublimes. So whatever reduction you get in the amount of aluminum metal you get is extremely small. So in the past, aluminum used to be an expensive metal because it required extremely high temperatures, and the amount of aluminum oxide that survived such high temperatures was so small that the amount of aluminum we were getting by carbothermal reduction was very small. So there was, like for example, 100 years ago, humanity never thought that today you'll be drinking Coke in aluminum cans and throwing them out. It just never occurred. Like just like if somebody tells you 100 years from now, people will be drinking Coke in gold cans, drink it and throw it. I mean, can you believe that? No. So what happened here? So there was a technique called Hall-Heroult process where they were able to take aluminum oxide, mix it with sodium aluminum fluoride, and this mixture can be molten, can be made molten salt, essentially molten composite, and about 1000 degrees, you can do electrolysis on this and you can get aluminum metal. So what happens is you take aluminum 3 plus 3 electrons, giving aluminum metal. So this requires the supply of electricity. Here again is an interesting point. For example, in Japan, electricity is more expensive than it is in the US. So although Japan needs a lot of aluminum, because of the cost of aluminum, making aluminum by electrolysis so expensive, even Japan today, even they do carbothermal reduction of aluminum oxide or the better yet, they import a lot of aluminum that we make into their industry. This is how the Aluminum Corporation of America, Alcoa, I don't know if you heard of it, if those of you who do invest in stocks, you might know the code Alcoa. So that's what we make. We make tons of aluminum supply all over the world, and we make a lot of money because electricity is cheaper. Okay. So these are all what we call metallurgy. So we use the electricity to extract the metals. On the top, what I'm showing you is the carbothermal reduction. It is still used. For example, magnesium metal, even today, is produced by carbothermal reduction. This process has an industrial name called Pigeon process. So each of these processes have different names. Hall-Héroult is the production of aluminum metal, and Pigeon process is the one that is used to describe the production of magnesium from magnesium oxides. All right, so the question then that haunts us is, why do different oxides take different temperatures? Why does aluminum take such high temperature, 2000, while zinc only takes 600 degrees? What is behind this mystery? So let's talk about this. All right, so there are two things that are happening here. On one hand, we have carbon getting converted to carbon monoxide, and we'll also talk about the metal, for example, X amount of metal plus half of oxygen gas, giving MXO solid. I'm showing both the reactions as if they are getting oxidized. Carbon is getting oxidized, metal is getting oxidized. What we are trying to do is we want to use the carbon to reduce this metal oxide to metal. All right? So let's look at the logistics of this reaction. What do you think the delta S sign for this reaction is? So we have a solid, a gas, half a mole of gas, right? Giving you 1 mole of gas. So the delta S for this process is going to be positive. How about for this? We have a solid metal and half a mole of gas is consumed. On the right hand side, we have no gases. So the delta S for this process is negative. Right? Now, if you look at the Gibbs equation, Gibbs tells us that delta Hg equals delta H minus T times delta S. So if you now look at the dependence of delta G on temperature, it is dictated solely by the sign of delta S. If the delta S is positive, like the case for carbon getting converted to carbon monoxide, your delta S is positive, which means as you increase the temperature, what happens to the delta G? Does it stay same, increase or decrease?
Decreases.
It decreases. Now, let's do the same thing for the next reaction, the metal getting oxidized to metal. Here, the delta S is negative, right? So what happens to the delta G as you increase the temperature? If delta S is negative, this is going to be positive, right? So as you increase the temperature, delta G also increases. So one way of doing this very nicely is what we call an Ellingham diagram. So let's see how that looks like. These are extremely important in metallurgical processes. So what you're plotting now here is delta G as a function of temperature. We all just agreed a minute ago that in the case of oxidation of carbon to carbon monoxide, because delta S is positive, the delta G will decrease as you increase the temperature. That's the kind of line that you see. So this is for the delta G of carbon monoxide. Now, if you were to do the same plot for the metal getting oxidized, so it will go like this. That will be the delta G for the metal oxide to metal. Now, here is the trick. If the carbon were to reduce the metal oxide to metal, then the free energy for the formation of carbon monoxide must be more negative than for the oxidation of the metal. Only then carbon can reduce. So this is a critical temperature here, where the lines cross, below which no reduction happens, above which you can see the reduction of the metal oxide by the carbon. So that temperature is the critical temperature. So if you were to treat the carbon with the metal oxide at temperatures below this critical temperature or the crossover temperature, nothing will happen. You won't get any metal. Because the oxidation of carbon to carbon monoxide is not thermodynamically more favorable than the oxidation of the metal. So if you now do this for multiple elements, you will see different materials having different slopes. For example, something will have a slope like this for the metal oxide to metal, in which case the crossover temperature is high. So different metal oxides have different crossover temperatures, and that's the reason why some oxides take extremely high temperatures for the reduction to happen. Am I making sense here, folks? I have included, I think, uploaded a file of the presentation where I have given extensive data of the Eilingham pictures. The idea of this lecture is to tell you the chemistry behind this. So this is purely the physical chemistry. It's just the free energy of the oxidation of carbon versus the oxidation of the metal, and use that free energy diagrams to understand exactly which one will reduce or what temperatures it will reduce. Am I making sense here, folks? Any questions on this?
How do you get the data for this experiment? I guess you have to do the experiment, right, to find it?
The heat of formation, right? The delta G basically is delta H minus T delta S, right? So delta H basically is the heat of formations. You can calculate the heat of the reaction by using the heats of formation. But one of the interesting things, I'm glad that you asked this question, between delta H and delta S, right? The delta H does not depend on the temperature as sensitively as the delta S does. So in other words, delta H is more or less temperature independent. That's the heat of the reaction. But the delta S is the one that controls, or the sign of the delta S that controls it. That answer your question?
Thank you.
Thank you. Yep. The next thing that we need to do is thermodynamics and answer everything. Well, I say no. I'm going to give you a couple of data. I want you to weigh on this using your own knowledge of the chemistry. For example, if I were to do this is the delta G for the reaction in which a chloride is getting oxidized to chlorine gas. And you know that there is no oxidation without reduction. In the process, the protons of the water are getting reduced to the hydrogen. Now the delta G for this process is 422 kilojoules. So can we calculate the cell potential of this then? Remember, cell potential and the free energy are related by delta G equals negative NFE0, correct? So we can use that equation, delta G equals negative NFE0. where N is the total number of electrons involved in the oxidation or the reduction. F is the Faraday's constant. Delta G is your free energy change, and that is your cell potential. So if you do this calculation, E0 equals delta G, which is 422 kilojoules. So we need to convert that into joules divided by NFE, where N here is the number of electrons. As you can see, 2 chlorides to chlorine, the net number of electrons changes to, so that's going to be 2 times 96,500. That is the Faraday's constant. So if you do this, the cell potential for this is going to be a -1. Why is the cell potential negative? Because the delta G is positive. In other words, the reaction is non-spontaneous, right? So if you do this calculation, you can do it at home. I did that just a few minutes ago. That came to about -2.2 volts. So here is the case. I'm using a salt solution that has chlorides, and I'm doing an electrolysis. And for the reaction here, the reaction is non-spontaneous, so you need to supply 422 kilojoules for the reaction to happen. That's a lot of energy. In terms of potential, that's about -2.2 volts potential. That's non-spontaneous. So if you apply 2.2 volts, you should be able to get chlorine gas. Without that, you will not get. All right. Let's look at, I have water here. So water also can be redox, can undergo redox process, in which case I have 2H2O giving H2 plus O2. My delta G for this process, I get about plus 414 kilojoules. So this is the potential or the delta G, free energy change for the splitting of water, and that's the free energy. So which one is more spontaneous? So if you were to look at those two reactions, which one is relatively more spontaneous?
The bottom one, I think.
Because it has slightly smaller delta G, right? Although both are positive, this delta G is smaller than the previous one. So one would expect then, when you do the electrolysis, you should get hydrogen and oxygen. To be fair, the potential for this, if you do the same calculation as I have shown you for the other one, it comes to about -1.2 volts. So when you do the electrolysis using sodium chloride and water, right, you would expect hydrogen and oxygen because the delta G for that is more favorable compared to the oxidation of chlorine. Surprise, surprise. When you do the electrolysis, you don't get oxygen. You get chlorine. So what's happening here then? Remember, in the previous classes, we talked about thermodynamics and the kinetics, right? So although thermodynamically, the production of oxygen is more feasible, kinetically it is not. Because the number of electrons required here is high, and there is something called Orr potential. So theoretically speaking, if you apply 1.2 volts, you should be able to get oxygen. That is the theoretical value. But in practice, you need to apply much higher potential. So that excess potential that you apply over and above the thermodynamically predicted value is what we call the Orr potential. The Orr potential for the production of oxygen is very high compared to chlorine. And for that reason, although oxygen production is thermodynamically more favorable, but kinetically, it is the chlorine that gets released. That's how we make chlorine industrially. We take saltwater or brine solutions to the electrolysis, and we don't see any oxygen. It is the chlorine at the anode and the hydrogen at the cathode.
So when you say over potential, like, does that mean the molecules have to move faster in order to do the reaction?
What happens is it is the electrode interface. For example, if you have the electrode here, right? That interface, very close to the surface of the electrode, the oxygen has to get produced, right? So in other words, oxide has to get oxidized to oxygen and then move out. So anytime you have gases forming in a liquid, see the gases form bubbles here. And those bubbles prevent the additional oxygen coming and hitting. In the case of chlorine, it's chlorine is more soluble in water than oxygen, right? So the chlorine does not make bubbles as extensive as does the oxygen. So for that reason alone, the chlorine gets reduced. They produced at the thing. One of the beautiful aspects of this chemistry is once all the chlorine is gone, once all the hydrogen is gone, what are we left with in the solution? So for doing sodium chloride, right? Na plus Cl minus electrolysis, all the chloride is getting oxidized to CO2, and all the water there gets reduced to H2. And if you look at the top equation, you also have hydroxides coming, right? For every 1 mole of chlorine, you get 2 moles of hydroxide produced here. That's not going anywhere. That's going to stay in the solution. So once you're done with the entire electrolysis of the brine solution, what are you left with in the pot? Your chlorine escapes the pot, the hydrogen goes away. So what stays in the pot then? How about the sodium, right? It stays back. Nothing happens to sodium because reduction of sodium is more energetically more expensive process than reducing hydrogen. So sodium stays and the hydroxide stays. So after the electrolysis is done, that pot is full of sodium hydroxide. This is how in industry they make 3 at the same time. They make hydrogen, they make chlorine. This is how chlorine is made commercially, just in case if you're interested in taking a brine solution and do an oxidation of that. And that's how you make industrial chlorine and the hydrogen. All right, so we get 3 at the same time. This is one of the beautiful concepts of electrochemistry being applied in real life to make gases. This is how we do industrially. This is what we call Solvay process, Solvay electrolysis of the brine solutions. Any questions on this so far? Okay. So I think we have covered a little bit of electrometallurgy. We covered a little bit of carbothermal methods of reducing metal oxides using elemental carbon. The next thing that we need to work on is to give you a brief review of what we call the oxidation reduction processes. So for that, we're going to look at some different reactions. So are you familiar with balancing the redox reactions from your previous classes? Suppose if I tell you once you balance this equation, what should be the coefficient of sulfur here? The reason I'm reviewing this is very important as we move forward in doing some more calculations. So remember, the first thing that you need to do is you need to find out the oxidation numbers here. Nitrogen is 5 plus, hydrogen is 1 plus, sulfur is 2 minus. This sulfur is 0, this nitrogen is 2 plus, oxygen is 2 minus. So clearly the nitrogen got reduced and the sulfur got oxidized here. Okay, so break it up into two half cells. So you get NO3 minus aqueous, making NO and H2S, giving S. So the next thing you do is, if you look at the top equation, any missing oxygen atoms are compensated by adding enough number of water molecules. I'm missing about 2 oxygens here, so I add 2 water molecules. Adding water gives you the additional problem of having protons. So those protons are compensated on the left-hand side by putting H plus ions. And once you are done with the mass balancing of the half cell, then you need to do the charge balancing. So we have 4 positive, 1 negative, that is net of 3 positives on the left-hand side. On the right-hand side, it is 0. So for compensation, you put 3 electrons here. That will give you the reduction half cell right there. That half reaction is now balanced both in terms of mass and the charge. We'll do the same thing for the next one here. So we need to add 2H plus here, the hydrogens, and we need to add 2 electrons here to compensate for the charges. That will balance both masses and the charges. Now, what you do is, you need to make sure that the total number of electrons in both the half cells are equal. Okay. So we need to multiply this by 2 and multiply this by 3. And when you add the equations together, you will get the final balanced redox reaction. Just to save some time, let me write down that one here. That equation comes out to 3H2S plus 2H plus 2NO3 minus, giving 2NO plus 3S plus 4H2O. All right. So the coefficient of water here is going to be 4. Coefficient of sulfur is going to be 3 here in the final balanced equation. So sometimes in the exams, even in the GRE, they give you through a redox equation as to what the coefficient of the balanced one is, because they want you to know the process, the half cells, how the electrons are moving from one to the other, and how do you make it equal. So when you're using the equation delta G equals negative NFE0, that N here refers to the total number of electrons you cancel in the final step. So for example, in this case, we cancel a net of 6 electrons. So for this reaction, N is 6. So I know that some of you know this already, but some others have told me that they were told a different way of doing it, but this is a good way of learning, because if you're getting into battery business and the construction of galvanic cells, it's good to have a good picture of this. Are there any questions on the balancing of these equations? Anything that's not clear? All right, okay. The next question that we're going to answer is the redox stability of the ions in water. So, if you look at the redox aspect of zinc, this one, the sub potential is negative 0.76 volts. This is the standard reduction potential. For those of you who have a rusted memory, basically all species are shown as if they are getting reduced, and you have a number called the cell potential, standard state cell potential, which is given as 0 here. That means negative 0.76. When the potential is negative, is it spontaneous or non-spontaneous? When the potential is negative, delta G is positive, right? Because delta G is negative in Fe, so the reaction is non-spontaneous. So zinc 2 plus will not spontaneously get reduced to make zinc metal. That's what that potential is telling you. However, in the presence of an acid, so for example, if I have 2H plus 2 electrons, giving H2, this standard state potential for the proton is 0, right? So now the question is zinc stable in an acid environment? To answer that question, we need to look at the overall potential, which is the reduction potential of the cathode and the anodes. Cathode is the half cell where the reduction happens. Anode is the half cell where the oxidation happens. So when you are looking at the zinc plus 2H plus giving zinc 2 plus H2 gas, if you want to calculate the potential for the whole reaction, you must have done this before. This is a very quick rundown summary of that. So you look at the species that is getting reduced, species that is getting oxidized. So in this case, the oxidation is happening at the zinc, reduction is happening at the protons. So when you look at the cell potential overall, the cathodic potential here is for the hydrogen to formation of hydrogen. That minus the anodic potential is negative 0.76 volts. So this is plus 0.76 volts. When the potential is positive, overall reaction, then you know the reaction is spontaneous. So what this tells you is, if you take zinc, put it in a solution that contains protons, the action will happen, and zinc is not stable in an acid. But the question is this. However, what happens if I put zinc in water? Would you expect a spontaneous oxidation of zinc to zinc 2 plus? What does common sense tell you? You must have seen bronze, right? Bronze has both copper and zinc. And if you take a bronze vessel, put some water into it, does the water get reduced to hydrogen spontaneously? If you have a brass vessel, or sprinkle some water on a brass knob, would you expect water to react with the brass? Brass has a lot of zinc. What does common sense tell you?
No.
No. Let's look at the process here. This is for standard state. What does standard state mean? This is what happens when all your aqueous solutions are 1 molar, that is the concentration of protons is 1 molar, and the zinc 2 plus is also 1 molar, and the temperature is about 25 degrees Celsius. What if that's not the case? In water, do you have proton concentration 1 molar? No. What's the concentration of protons in water approximately? If you have neutral water, it should be 10 to the negative 7 molar, right? Yeah. So what happens now? The potential, would the potential change? Let's see what happens here. Let me see this. So 2H plus 2 electrons giving H2 in the standard state is 0. What means the concentration of this is 1 molar and hydrogen is 1 atmosphere. It's a standard state. Now, when you go to water, what happens to the concentration of H plus? Is it 1 molar or is it less? If you take pure water, the amount of protons in pure water is very small, right? 10 to the negative 7. That's why the pH is 7 for pure water. So when you reduce the concentration of H plus, which way would the equilibrium shift?
To the left.
To the left. When the reaction goes backwards, is it becoming more spontaneous or less spontaneous?
Less spontaneous.
Less spontaneous. So what should happen to the potential value? Should it increase or decrease?
Should decrease.
Should decrease. You're absolutely correct. You know what? That value is negative 0.44 volts. So this is the standard state potential, which is 0. But at pH 7, that potential now becomes negative. I'm also giving a reason why that is negative, because we are reducing the concentration of the reactants. Reaction moves backwards, becomes less spontaneous, and that is what is reflected in the more negative value of the cell potential. Now, if I were to add zinc to pure water, and then look at the reaction again here, your overall cell potential is still cathode minus anode, except this time we don't have standard states. So your cathodic potential now is negative 0.44 volts minus the anodic potential is negative 0.76 volts. So what should be the value here? This should be plus 0.32, right?
Yes.
That is plus 0.32 volts. So what does it tell you about the spontaneity of the process?
It's spontaneous.
It is spontaneous. But you know, from your experience, right, that doesn't happen. Although thermodynamics tells you it happens, but you don't see that happening.
You have to provide heat and then it'll happen like slowly.
No, we're not talking about heat. This is standard state conditions, right? 24 degrees. I'm doing both reactions, like I'm dropping a piece of zinc in acid and dropping a piece of zinc in water. In acid, the reaction is so spontaneous, it just takes off very quickly. But in water, even if you leave it for 1,000 years, it's not going to happen. Unless, of course, you heat it or you stir it or you do things. Why is that? Here is the most important part of the electrochemistry. That is, when we have acid, the potential difference is 0.76. When you have water, that potential drops to 0.32. Whenever you have gases coming out, unless the potential difference is greater than 0.6 volts, don't quote me on this, 0.6 is about the rule of thumb that everybody agrees. That difference, unless it is greater than 0.6, no reaction will happen. That is because of the ore potential issues. So whenever the gases are produced in electrochemical processes, you have to deal with this monster, that is the ore potential. For that reason alone, zinc will not react with water because of the ore potential. So the question then is, how do we reduce the ore potential? One way to reduce the ore potential is to make the zinc metal extremely fine. Make it like a dust. if you have zinc dust and if you put it in water, that will react and produce hydrogen, but not solid zinc. There's an interesting case that happened in New Jersey some time back. In Edison, we have a plant that is called galvanization plant. What they do is they take the iron beams and they coat zinc on top of it. And the efficiency of the process is hardly 1-2%. Most of the zinc drops down in the form of fine powder. So what the company does basically is they take this powder, put it in a truck, ship it to Texas, make the bricks again, come back and use the bricks. All right. So it so happened a few times a year, when the trucks were passing North Carolina, they were catching fire. The trucks were literally on fire. And they had no idea what was happening. All right. That was the zinc powder. So when the experts put down all the facts together, they found that the trucks must have passed a rainy day. When it rains, the humidity inside the truck must have been very high. And if you have finely divided zinc, which is zinc dust, zinc powder, that reacts with water to form the hydrogen. And once you have the hydrogen in a closed container, after some time, it acts like a bomb. So any spark, it will just ignite it and, it'll just throw the bulk out. So not knowing that is the reaction, the fire marshals came to the company and inspected, and they found carbon monoxide. And the company was telling them, look, we don't use any carbon. There is no way we can get carbon monoxide. So essentially what happens is the sensors that they use, the fire marshals use to detect carbon monoxide can also detect hydrogen. They didn't know that before. So apparently, finally, what the result is, when you have finely divided zinc, even if the potential is 0.32, your over potential is reduced to a very small value, maybe 0.15, which is much smaller than the value here. So the reaction happens spontaneously. There's a lot of research going on today in the world in terms of reducing this over potential. As you all know, there's a lot of push on making hydrogen from the electrolysis of water. One of the biggest problems is the over potential of the oxygen. If you can bring down the over potential, you will make billions of dollars. I'm not kidding. The people are improving. I mean, they have, in the past it was 0.6, but now it comes to about 0.2 volts. But still, that's not enough. The industry wants it almost close to zero. And there is only one metal that can give that over potential close to zero, that is platinum. But platinum is so damn expensive. So people are now trying to find alternate materials which are as good as platinum, but cost much less. All right? So that's entirely different research area. But the reason I bring this up is because this is how you look at the overall processes. Okay, folks, I'm sorry we have lost about 10-15 minutes because of the internet issues. But definitely next Thursday we'll pick up where we left, and we're going to talk about the stability of inorganic species, which one will be easily reduced. Like, for example, if I have a perchlorate and a hypochlorite, which one is easily oxidized? Which one is more stable in water? So these are all the issues. We'll be getting into that. All right. Again, I apologize for the intermission that we have had. We will see you again next Thursday.